Lastly, a few words about multi-class classification problems. So here, this has nothing to do with multi-class evaluation metrics. It's just how certain classifiers can be extended to work with multiple classes. In this class, we talked about decision trees, k-nearest neighbors, gradient boosting random forests, and other classifiers that all work with multi-class settings naturally. However, in your future studies, you may stumble upon other types of classifiers like logistic regression or support vector machines that are naturally more designed for the binary classification. However, there's a special case of logistic regression. It's called multinomial logistic regression or softmax regression, which is a topic that is covered in the beginning of Statistics 453 next spring semester. It already supports naturally multi-class classification. But let's maybe consider a case of support vector machines, or let's say perceptrons, which are classifiers only for binary cases. So how can we deal with that? So here's one approach how we can extend any binary classifier to a multi-class setting, and that is somewhat related to the average per class accuracy that we talked about, or the balanced accuracy. So consider you have these three classes here, the yellow circles, the red squares, and the blue triangles. So what you can do is you can divide that problem up into three separate classification problems. So it's also then called one versus rest, or OVR. Some people also call it one versus all, OVA. So these are two just different words for the same thing. So what we are doing is we are splitting this task up into three subtasks. So here we are in the first subtask, considering these as one single class. So this is, let's say, our negative class, and this is our positive class. And you can see then we just try to classify these correctly, and then we do the same thing for the other classes. So in the second case, now these are our negative class. Let's call them negative here. These are our negatives. And then here on the left side, we have the negatives. And we would then have essentially three binary classifiers. So the number of binary classifiers is equal to the number of classes in the dataset then. And in practice, we would, during training, fit all three classifiers. And during prediction, for each training example, we would run all three classifiers, and then we choose the one that gives us the highest confidence score. So in that case, for example, in the k-nearest neighbor case, if we have, let's say, let's pick a 3 nearest neighbor case. So if we have, let's say, this data point here, the 3 nearest neighbors, could be, let's say we would predict the case that is not in the training set, this case, and we would have the 3 nearest neighbors as these. So here we have 2 yellow ones over 1 square one. So we have with 1 square one. So we will have as a 2 out of 3 score in favor of the circle here, because that's the majority here in the neighborhood. So, and then we would repeat the same thing for the second case here. So we would pick this one, and now we would have these here as neighbors. So they are all treated the same. They are all treated as the negative class. So we have a 3 over 3 as negative class, but that's not useful because it doesn't tell us which class it is. We only know it's a negative class. And then we would, in this last case, consider this one. So let's say we have these as the 3 neighbors. So in this case we have one red one, and 2 negatives again. So here we have a 1 over 3. So actually we can consider this also as 0 over 3. So in this case, we would predict this point here, let's call it a question mark point, because we want to predict that. In this case, we can consider this, we would consider this with the highest confidence score. This is a confidence score of 2 over 3, 0 over 3, and 1 over 3. We would predict then the one with the highest confidence score, which is this yellow circle. So for this data point here, which might be here, if we look at it, this one would be predicted a yellow one. And yeah, we would do that for every classification data point. So in this case, this is a technique for extending binary classifiers to multi-class settings. Another technique is 1 versus 1. So here we are fitting more classifiers than the number of classes. So in fact, we are if we have 3 in this special case, we would have also 3 classifiers. So the number of classifiers we fit is number of classes times number of classes minus 1 divided by 2. So these are all the combinations. That's the way you compute the combinations of all possible classes if we only have a binary classification setting. Again, we are reducing a multi-class setting to multiple binary classification settings, but before we set all the other classes to rest or other or negative classes, now we are just excluding them at each step. So you can see, for example, in the first one, I pick the triangle and the square, but I exclude the circles. In the second case here, I have the yellow circles and the triangles, but I excluded the squares and so forth. So in this case, I'm excluding those where these are not in the combination. So I consider all the possible combinations, which is the number of classes times the number of classes minus 1 divided by 2. And yeah, just a silly question, the big O of that, how expensive it is if we have a large number of classes. So in terms of the number of classes, it would be big O of number of classes squared, right? So this would be number of classes squared. So this is actually a pretty expensive algorithm to run if you have a large number of classes, because you create all these binary tasks. So maybe let's spontaneously look at an example here. Let's say we want to classify a data point that is located, let's say, here. So in this case, we would consider the majority vote. So how this works is we would train each of these classifiers, but then during prediction you'd use a majority vote. So in this first case, it would predict this one because it's on the left side of the boundary, right? So, and then in the second case, we are approximately, let me draw that everywhere here. We are here and maybe also here. So in this case, we would predict this one because it's closest to these if we would use a k-nearest neighbor again. And then on the last case here, we would also predict this one, and then we do a majority vote, and the majority here is this yellow circle. So for this question mark data point, we would predict a yellow circle by majority vote. It's more expensive though than in the previous case, because if we have a large number of classes, we would have a larger number of classifiers. For the case of 3 classes, it doesn't make a difference. In both cases, we have 3 classifiers. One advantage of this method though, even though it can be more expensive with more classes, is that it doesn't create a class imbalance. So if I go back one more time, you can see here I'm actually creating a class imbalance, right? Because now I have 3 data points from one class and 6 from the other, right? So I'm creating a class imbalance, which can challenge some classifiers in terms of how well they learn. Here I keep the same class proportion as in the original data set between the 2 classes, right? So in that case, I'm not creating such a new stark class imbalance. Okay, but this was just explaining how binary classifiers can be extended to multi-class problems. What we are more interested in the context of evaluation metrics is how we can extend binary classification metrics to multi-class settings. So 2 common ways for doing that is the so-called micro and macro averaging. So what we are doing here is, so if you recall, first of all, the precision is computed as the true positives divided by the true positives plus false positives if we have a binary classification problem. But if we have more classes, like classes 1 to C, for example, 2, 3, 4, 5, 6 classes, there are 2 different ways for computing the precision. So this is maybe easiest explained by taking a look at the balanced accuracy slide again that I made a while back when I was talking about the average per class accuracy a few videos ago. So what we did is we took this confusion matrix here and created these binary confusion matrices. So in each case we had a positive class, which was either class 0, 1, or 2. And then we had the remaining 2 classes in each case as the negative class. So here now we have the true positives like this, and then the false positives like this. And for each case we can then compute the true positives and false positives. So in this case this would be TP1, TP2, TP3. And this is where these numbers come from. So we can compute the true positives for class 1, class 2, and class 3, if we have 3 classes, for example. And then compute the precision by dividing it respectively against or by the true positives and also false positives. For the false positives, again, we can get them as follows by computing the false positives for each case here. And this is how we would compute the micro precision. And similarly we can compute the macro, or not similarly, but there's another way we can compute the precision. That's macro averaging. So in macro averaging we would first compute the precision for each class, and then we would compute the averaged precision by averaging over these precision by the number of classes. So in that case we would compute the precision for class 1, the precision for class 2 as positive label, and the precision for class 3 as positive label, and then average over these two, like adding them together and then dividing by 3. This would be our macro averaging. Both are acceptable ways of doing that. So micro averaging is more useful if we want to weight each instance or prediction equally, whereas macro averaging weights all classes equally to evaluate the overall performance of a classifier with regard to the most frequent labels. So there are just different approaches for doing that. So how do we do that in scikit-learn? So if you use the precision score in scikit-learn, and the same thing also applies to the recall and F1 score, and if you have more than 2 class labels in the test set labels or the true class labels and the predicted class labels, then you will get an error if you just run the precision recall. So if you call it just like this and you have more than 2 classes, then there will be an error, and it will ask you to specify for the average here something like micro, macro, or weighted. So micro and macro are the ways we talked about just in the previous slide, how these are computed. So you can set that to micro or macro, and there's a newer way, it's called weighted. So it will also consider the number of true instances at each label, accounting for the class imbalance. So it's similar to macro, but it's also, when I understand correctly, dividing by the number of labels. So, which is essentially very similar to what the average per class accuracy is doing. All right. And then there is also the receiver operating characteristic area under the curve score. So in the previous video I mistakenly said it's just ROC underscore AUC, but the function for computing that is ROC underscore AUC underscore score, and this one also has the averaging, and it's by default set to macro. Okay, so the weighted is actually useful for dealing with class imbalance problems, and another way for dealing with class imbalance problems is using algorithms for over and undersampling. So for example, if you have an underrepresented class, you can oversample the underrepresented class to have more examples of that. It can sometimes help. Scikit-learn also has a class weight parameter for most classifiers, but another way of dealing with class imbalance is considering more sophisticated ways of creating artificial data points. For example, one is called SMODE, But in this class, we won't be going into too much detail about any of these because, we are reaching the end of the semester. So if you're interested, there is a library called Imbalanced Learn, which is compatible with Scikit-learn, which contains more variants of dealing with class imbalance, and it has a very good documentation where you can find some short discussions and how these methods work. So, but with that, unfortunately, we are reaching the end of the semester, and I don't want to cram more topics into this last lecture because, like I said, you are probably busy working on your homework and doing your presentations and submitting the presentations by Sunday, so that I can then put together the presentation pages for next week. So in that way, I don't want to take too much of your time. I just wanted to say it was a pleasure teaching you this semester, although it was a little bit weird. I appreciate everyone stopping by during office hours. It was always good to have someone also giving some feedback about the lectures and asking questions and talking about things. I know that also many of you are in different time zones though. So for those who, for example, didn't have any questions that you wanted to ask in person or couldn't attend, I also appreciated when you were writing comments on Piazza. So that was also great. So I will probably, before I say goodbye here, I will see you again during office hours tomorrow, and also will probably record some short videos next week, introducing the different class projects and how the voting works and stuff like that. So it's not that you have heard me for the last time. So we will be in touch, and there's the whole next week with the class projects that I'm really looking forward to. And with that, we covered model evaluation, which I think is an important topic because you will be probably going out there into the world and learn about many more additional algorithms that we haven't covered here in terms of classification algorithms and regression algorithms. So here you have, at least for the classification algorithms, for the typical machine learning case, a whole set of techniques that you can use to compare them to each other to find out which one is good for your problem. I know based on my interactions with many of you that many of you are also considering going into industry, and there it's also often about the performance of an algorithm. You want to solve a problem, and how do you compare algorithms fairly? So here at least you have a selection of techniques, and in addition to that, we didn't really get to that in this course because we can't cover everything. I mean, the machine learning field is so big, we would have at least 10 courses if we want to cover every topic in machine learning in great detail. But if you recall, Christoph Molnar's book on interpretable machine learning is also a really recommended read. I posted this earlier. So which is a book that talks about different model interpretation techniques, which is also important because it's not all about accuracy or performance in terms of precision recall, receiver operator characteristic under the curve and so forth. Sometimes it's also very important to have a very interpretable model so that you can understand when it makes mistakes. And this book also outlines some techniques for doing that. So as a future study topic, if you are wondering where to go from here, I think the interpretable machine learning book would be a good read. It's available online for free also. If you lost the link, I'm happy to post the link again. I will probably post it under the video if I don't forget. If I forget, remind me. And we have next spring semester, I'm teaching statistics 453, which is a deep learning course. What it has in common with this course is that it is about classification and supervised learning. Most of it will be unsupervised learning, but a totally different set of techniques. It will be about deep neural networks, which is very different. It's a little bit more challenging because we don't have scikit-learn for deep learning. We have other libraries which also are easy to use. However, based on the nature of neural networks are a little bit trickier to implement. But you will see if you are interested in that class, it's not that complicated. And it's a whole different world of machine learning, deep neural networks, which is also super interesting. However, just briefly summarize this again, machine learning and deep learning are kind of for different application areas. Machine learning is usually when you have smaller data sets, mostly the tabular data sets, where you have a domain expert designing the features, for example, as we've seen in this breast cancer data set. However, in deep learning, we usually apply these algorithms to raw data, for example, raw images or raw text and so forth. However, for that you need way more examples. So you need larger data sets and so forth. So in that way, the application areas are very different, because some people sometimes ask, what is more important, machine learning or deep learning, and which should I learn? I would say, both have their applications in the real world. It really depends on what problem you're working on, and ideally, you have a repertoire of different techniques. And even if you're working on deep learning, it's always good to have a traditional machine learning classifier as a benchmark, as a baseline, even though, let's say, it's an image data set, because you always want to see or use a simpler method first, like a method that is easy to implement before you do things more complicated. Because also with deep learning, it requires way more babysitting. You have to look that the training converges. You usually need more expensive hardware, GPUs, and so forth. So it's not trivial to run. And even though you may have a big data set, it might be too expensive. Then also, traditional machine learning is also something to consider. But sorry, I don't want to have a long monologue here at the end. So I will see you, I would say, next week when we have the project presentations. I will probably say hello in some of the videos to introduce the different projects and how this procedure works. So with that, have a good rest of the week.